Okay, so as I mentioned at the end of the last video, in this video we will study textbook section 3.2.2 on the omitted variable bias formula and section 3.2.3 on bad control. So I have done this in class, but I will show you an example from table 3.2.1 at the end of the explanation. Okay. So the first topic is the omitted variable bias. What happens? So we learned we need conditional independence assumption. That's our intermediate conclusion in the last review. But what happens if you do not include x, right? Then conditional independence would fail. To study that, we have to think about different equations, and we will study the relationship among those equations. Okay, so without observing x, suppose that you don't observe x, right? Then you are going to estimate on a simpler regression equation by regressing outcome only on the treatment, right? So you should have had on variable here, but that's not observed. So you end up like this. So you wanted to estimate this. This is the ideal, the true equation, but you could not observe this part. So you end up with a shorter equation. So then we would like to compare this coefficient mu. So you wanted to estimate rho from this regression equation, but it is not available, and instead you only do this and you only estimate mu if this coefficient is different from this coefficient. Then that is a bias. Yes, there is a bias, and that is the omitted variable bias. So let's study that. To study that, we will specify how the unobserved control variable is generated, like how this is related to the observed variable. So I will assume that the unobserved variable is related to treatment this way. Actually, in an earlier slide, I told you the other way. D is determined by x, but for mathematical algebraic convenience, I will change their positions. Okay, and then plug this equation back into the ideal regression equation. Then you are going to get this equation. Pretty simple, right? This is the true original ideal regression, and x can be written in this way. And what I'm going to do is I will rearrange this equation into intercepts, constants, plus a term factored by d, right? And then error term eta and epsilon. So categorize or classify into 3 terms, and then this will be what you're going to estimate, rho plus beta delta. So the coefficient of d will be this guy, and this will be your new intercept. This will be your new coefficient. This will be your new error term. So something is wrong by this much. So plus beta delta is the bias because you could not observe that arises because you could not observe x. Okay, so this is the omitted variable bias. So it is not that surprising. You did not observe something, so your estimator is wrong. That is not that surprising. But we have to think about then what we can learn from the estimate. Even if I know my estimator is wrong, still it may be informative. That's when you can tell the sign of the bias. So if you can tell if your estimator is overestimating or underestimating, then at least you know which side the truth lies, right? It's a right. So here is an example. The outcome is salary or income or wage, whatever, yeah. And D is education. And suppose that X is intelligence, but it is unobserved. So your wage depends on your education and your intelligence, but you do not observe the intelligence. In this case, think about this. Your intelligence and your education. I expect a positive coefficient delta because the higher educated, the more likely to be intelligent, right? So delta should be positive. And obviously, beta should be positive. The more intelligent, you should make more money, right? So beta must be positive and delta must be positive. So the bias beta times delta must be also positive. So what you estimate is greater than the truth by this much. So you are overestimating the true coefficient. That's one actually can be useful, potentially useful information when you do like analysis. Okay, here is an example from the textbook. Let me show you the textbook table. Textbook table 3.2.1. This is these are estimates of the returns to education for men in the National Longitudinal Survey of Youth, right? Data are from this data set. By the way, you are going to use this data set in homework 3 or homework 4, right? And you are going to replicate this table, so pay a little bit more attention. So sample size is given, and parentheses inside in the parentheses are standard errors. But we will first you need to understand what these columns imply. So simply speaking, in this table there are 5 regression results in one table. So there are 5 different regressions are estimated, but only the coefficient of D is reported. Like, coefficient of D is reported from 5 different regressions. But the difference between those regressions are the set of control variables included in the regression. Okay? So, for example, in the first regression, no control variable is used. That means simply the income, here, log wage is regressed on years of schooling. That's it. Then you get some estimate that is 0.132. So this means that you can interpret this as additional one more year of education of one more year increases your wage by 13.2%. 13.2% is the returns to 1 year education, right? Increase in education by 1 year increases your wage by 13.2%. Okay? So that is the simplest regression without any control. And as we discussed, this must be biased. Like I considered intelligence as an omitted variable. So if you agree with that, intelligence is an omitted variable. So following the same logic we discussed earlier, this this estimate must be overestimating. It must be an overestimation, right? Because we know that the omitted variable bias should be positive. Like, let me enlarge this. Okay, so this must be overestimation. So that means the true returns to education should be at least smaller than 13.2%. Okay, that's what you can get from the first regression. But now, what I'm going to do is, intuitively speaking, the problem arises. Oh, excuse me. The problem arises because the education is not randomly assigned, and the unobserved intelligence is an omitted variable. So what we are going to do is we will include, even though we do not observe unobserved intelligence, we can include some variables, observed variables, that are related to intelligence. Okay, that's what we are going to do. If you include more variables, then the omitted variable bias will be reduced because some part of the intelligence will be explained by the included variables. So in the second regression, we include age. As a result, the estimated returns to education change it from 13.2% to 13.1%, which is actually a pretty small change, statistically insignificant change, right? That is because age does not help explain intelligence. Age has nothing much to do with intelligence, right? So that's the problem. Including age does not control for the omitted variable. So the change is pretty small and insignificant. And next, in the third regression, we try more variables. And these additional controls include mother's and father's education and dummy variables for race and region, like whether you live in like central or northeast or southern area, west coast, like that. Okay. In particular, the key variable must be mother and father's education. And then it's clear that these variables must be a good variable to explain the unobserved intelligence. Parents' education is an important indicator of your intelligence. So as a result, the estimate changed a lot from 13.1% to 11.4%. It dropped nearly by 2% point, which is quite significant. Some change. And we may interpret this as a reduction of the omitted variable bias because we included parents' education, and this variable like explains some part of the unobserved variable. So that much omitted variable bias is removed, can be controlled, right? So that is 2%. However, still the parents' educations cannot be 100% perfect to explain unobserved intelligence. So I guess some unobserved bias still remains in this estimate. So this estimate should be better than the earlier ones, but I guess this variable cannot be perfect. So in the next regression, we include AFQT score. This is a standardized test for armed forces qualification test. So it's like your general test for your ability, like not only about your intelligence, but your like skills, basic skills, like you know. So it is a very nice and standardized, comprehensive test score, which is a very good measure of your general ability, or ability and intelligence, right? So I believe this test score is a significantly important variable to capture the ability. So as a result, the returns to education changed from 11.4% to 8.7%. It drops like nearly 3% point. So that means also a large part of omitted variable bias is reduced by this test score, because the test score could capture the unobserved intelligence. So you are getting closer to the conditional independence assumption, right? Ideally, you want to have the perfect intelligence variable. Instead, you explain the intelligence using other variables, proxy variables, so you are getting closer to the truth. That's what practitioners do in practice, because like data limitation cannot be overcome. You cannot do anything like in collecting data. So given the data and given the variables, we try to get the best result out of it. Okay. So as I said, these four results are actually from different regression results, and only taken only one number is taken from one regression. The last regression will be discussed after at the end of the next video, because it's not about omitted variable bias, but this regression is related to the bad control example. Okay. Let me see if. So this is exactly what I just explained. So yeah. So the bias. This example shows the proof that it shows that the omitted variable bias was positive as we expected. Okay. Okay. Thank you for watching, and I will continue in the next video.